Okay, in this tutorial we're going to learn how to write a custom GPU module and run it from Python. So first let's begin by writing the CUDA kernel code. So that's going to be in a .cu file. So we need an external C function called sum, and we're going to add the elements of two vectors and store the output in a third vector, and we also need the number of elements n. Okay, so now we need the index number. This is a one-dimensional kernel. It only looks at the x index. Let's see, it should be x. So if I is less than n, then we perform the sum. Okay, so let's write a little makefile to make things easier. So we need to compile this CU file into a PTX file. And to do that, we're going to use nvcc. Okay, so we need to provide the CUDA include directory. And since this is a 64-bit machine, we need to generate a 64 PTX file. Okay, so we need to specify the architecture. So this is a GTX 1080 machine, or this machine has a GTX 1080 GPU. So this is a supported architecture for that GPU. If you have a different GPU, then you may need to look up what are the supported architectures. Okay, let's try to make... Okay, so now we have a PTX file. Alright, so now we need to write a C++ and a header file that are going to call this kernel. So let's start by writing the header file. Let's see, we'll call that code.h. And basically here we're going to write the function declaration, function prototype, define, these are our header guards. Okay, so we need to include a vector and define the function prototype. So the function is going to take two vectors as input and return one vector as output. Okay. And now let's write the CPP file. Code.cpp. Okay, so now I need to include a whole bunch of things. include code.h, which we just defined, and then include some CUDA stuff, CUDA.h. Some helper functions. Okay, and we need to specify the namespace. So we're using namespace std. Okay, vector float sum, vector float input. Okay, so we're going to make the assumption that this input vector contains two other vectors, and each of those two vectors has exactly the same size. So that's going to be n. Okay, and then we need to know the number of bytes, since we're going to be using a lot of binary copying, memcpy. Okay, so let's declare some CUDA objects, such as CUDA device and CUDA context. And module. And function. Okay, and now we need to define some arrays. And some device pointers. So these arrays are on the computer memory, on the RAM for the machine, and these are the arrays for the GPU. So this is GPU memory. Okay, so first we need to call cu init. And then we need to find out the device ID that we're going to be using. So this machine has only one GPU, so I could have just hard-coded 0, but in case your machine has multiple GPUs, this way you can see which GPU the program is actually going to use. And by the way, you can get a lot of this code from the CUDA samples. So if you want to get started, if you install CUDA, then you can go to the samples directory, and there's a lot of samples there. Okay, print out some debugging information. Okay, so now we need to get the device. See, device get with that specific ID. And now we need to get the CUDA context. And now we need to load the module. So that PTX file that we generated earlier, that's the module that we're going to load. Module load. And as you recall, the module is called sumkernel.ptx. And now we need to get the function that's defined here. And the function is called sum. Okay, so now we need to allocate some memory. So I'm using malloc here, but you can also use new. Malloc is more of a C convention. Okay, so now we need to copy the contents of our input vectors into HA and HP. Okay, and now we need to allocate the CUDA memory arrays. DA, DB, DC. And we need to copy from HA, the host memory, into the DA, which is the device memory. H to D means host to device. So this is the destination, and this is the source. And now we need to prepare to launch our kernel. So to do that, we need the threads per block, which we're going to specify as 256, and we need the blocks per grid. So this is this defines how the CUDA threads are partitioned among the indices in our array. So threads per block means that there are going to be 256 threads in one block, and the number of blocks is going to be the total number of elements in our vector divided by the threads per block, and this just rounds it up. Okay. So we need to specify the arguments, which are going to be our arrays DA, DB, and DC. So it's these arrays here, and we need to specify N. Okay, so now we can run our kernel. CU launch kernel, some kernel. So this is a one-dimensional kernel, so that's why these are ones here. However, if you have a three-dimensional kernel, that is, you have X, Y, and Z here, then you can specify 3 threads per block and blocks per grid. In that case, it would be threads per block X, and blocks per grid X, and then Y, and then Z. Okay, and now we need to synchronize. So this ensures that the GPU is finished running this kernel before we can proceed with our CPU calculations. Okay, so at this point we need to copy the result from GPU memory into CPU memory. So CPU mem copy device to host. Okay, and at this point we need to create a vector, since this function returns a vector. So we need to create a vector and then push all these output elements into it. So vector sums, and we'll resize it to have n elements, and then copy into sums from HC. Okay, and then we need to do some memory cleanup. So clean up all the GPU memory. And then clean up all the CPU memory. Or all the RAM memory. So FHA and free J BC. Okay, and then we can finally return sums. Okay, so this is the C++ function that's going to run this GPU kernel to add up all the elements in these two vectors and then return the result. Okay, so now we need to compile it. And to do that, we go into our makefile, and we're going to use G++. We need to specify the CUDA include directories. Specify the object name, code.o. Okay, so let's see if this compiles. Okay, so that compiles without errors. and we see this code.o file that was generated here. Okay, so now we need to write a swig file. A swig file basically allows Python to know what the function name is called and what the arguments are. So let's see. I'm going to call it code.i. Okay, so here I'm going to declare this module code. Okay. I. So now we can compile the swig file using swig, which you can install using pip. So you can do pip install swig. Code.i. Okay, so let's see if that works. Okay, so that generated code.py and codewrap.cxx. So now we need to compile the codewrap.cxx into an object file, codewrap.o, and then we're going to add all our object files into a shared library, .so library. Okay, so now here we're going to compile our codewrap file. And we need to specify the Python include directories. So I use Python 3.5. This should be L. 3.5. Okay, let's see if that works. Okay, so now we have these two object files. Okay, and now we're going to generate our shared library. Code.so. And the shared library is going to contain our two object files. And also we need to specify the CUDA library. CUDA. Okay. So let's see if that works. Okay, so we have our shared library, code.so. So now we can write a Python file. So we call it test sum.py. And here we're going to import our code library and declare our input. Okay, and then we can call our function and print out the results. Print B. Okay. So now, if we run Python 3 tests on py, then we see that indeed we have summed the elements from our two vectors. So 3 plus 3 is 13, 5 plus 10 is 15, and 7 plus 12 is 19. So that's it. That's the end of the tutorial.